Last talk of the conference, our second speaker is Roei Kisous from the Technion. Roei is finishing his master's and started working in Huawei.
Thank you. Okay, so I'm going to talk about our paper, the What Formula 2, the migration games in the duplicated system. It is a joint work of Ariel Kolikant, Gala Edgar, and myself from the Technion, Avinav Dugel from Delhi FC, and Sarai Sheinwald from Old Browder. So we all know what the duplication is, and we are now going to talk about file migration. The context in which we are going to talk about is a distributed system in which we have many different servers, and we refer to each server as a volume. Inside every single volume we have its own metadata and blocks and so on and so on. So we are going to talk about file migration, and more specifically how we transfer files along with our blocks between different volumes. So for example, if we have the following system and we want to transfer file 2 from volume 2 to volume 1, we basically move its metadata along with its blocks. So B1, B2 and B3, the three blocks will be moved into volume 1. So now we're going to talk about the file migration in the duplicated system. So in this case, as we said before, each volume contains its own unique set of blocks, physical blocks, and we have each server implementing the duplication within itself. So in this case, if we want to migrate, to move file 2 from volume 2 to volume 1, what actually happens is a bit different. So we'll first look at B1. B1, the blue block, is a part of file 2, so we need to move it to volume 1. But because file 1 already has this block, we do not need it. We don't need to move it. We can just use the same block that already exists on volume 1. So the blue block B1 from volume 2 can be deleted. As for the second block B2, it needs to be moved because we don't need it on volume 2 anymore because file 3 do not use it, but we do not have it on volume 1 with file 1, so we need to move it to the destination. As opposed to those two blocks, we have B3. B3 is used by file 2 on volume 2. So when we want to move it along with file 2 into volume 1, we need to replicate it because it doesn't exist on the destination. So these are the three states that we can reach when we move files along with their corresponding blocks. So basically, in our study, the main purpose that we wanted to achieve is to create an efficient migration plan. And a migration plan is basically which files we need to move and to which volumes. So as part of this migration plan, we had three different goals. The first one is the minimization of the system size. We wanted to make the duplication as efficient as possible, and in order to do that, we need to make use of this. So the second goal that we have is to minimize the network traffic that we consume during our migration plan. This is done basically because we do not want to move the entire system over our network, and this is also, it can be limited resources. So the third goal that we have is to balance the volume sizes. This is mainly here because we do not want, because we have a distributed system, we do not want one volume to contain almost all of the files that we have in the system. So when we balance between the different volumes in the system, we prevent this situation from happening, and we achieve the goal of distributed system. So all those three goals are part of our study, but the main point is that those three goals are conflicting. So if we want to minimize the system size as much as possible, we need to make the duplication as efficient as possible. We need to put the entire system inside one server, inside one volume. But if we do that, we violate the principle of balancing between the different volumes, because we will have only one volume that has the entire data. So we addressed it by deciding that the main goal of our approaches will be to minimize the system size. This is our main goal. And the other two goals that we had, we refer to them as secondary goals, or even constraints in some cases. So during our study, we showed 3 different approaches. These are the 3 listed here. They are listed by order of complexity. So the first one is the grid heuristic, which is a very simple one, and it's the most, it is less complicated than the other. The second one is the hierarchical clustering, which is a bit more complex, but it is not the most complex that we can see here. And the third one is the ILP, the integer linear programming approach, which is the most complicated approach that we had here. And the question that rises from those from these future comparisons is, does higher complexity guarantee us a better migration plan? Does ILP, because it is the most complex approach, guarantee us the best migration plan that we can achieve? So the first approach that we had is the greedy approach. Basically, it's an iterative approach that maps a file in each step between the different volumes. And our 3 goals are presented right here, and we want to address every single one of them. The first one is to minimize the system size. This is done by a capacity reduction step, and this is not something new. It was shown on FAST19. Basically, it takes the file that it takes a file to remap between 2 different volumes that will reduce the system size by the most. The second goal that we had, to minimize the network traffic, is addressed by an halting condition. So when we reach a certain amount of traffic that we set before, we stop the process, and therefore we do not consume more network traffic than we originally wanted. The third and last approach, goal, is the balance between the volume sizes, and this is done by another thing that's called the load balancing step. This load balancing step is another step that takes place in between other capacity reduction steps, and the main purpose of it is to take a single file from a very large volume and move it into a small volume in order to balance the system size and prevent it from having the entire files on the same volume. You can read more about in the paper about how we iterate between the 2 steps, how we remap at all, by which conditions. All of this is presented in the paper. Our second approach is the clustering approach, which is basically grouping similar files together. Because we want files that have high similarity in the same volume, we basically want to merge those files. And at the end of the process, we have a few clusters, which every cluster then assigned to a different volume. So the 3 goals that we had is addressed by the following steps. The first goal, the minimization of the system size, it is addressed by Jaccard index. Jaccard index is a type of similarity, a measurement that measures the similarity between 2 files blocks. So when 2 files share a significant amount of blocks, we will have a very high similarity, and we will want to merge them together into the same cluster. The second metric that we had is addressing the traffic network. When we use only the Jaccard index, we might not consider the original volume of each of the files, and we do want to use that because we do want to keep in mind that we can't use the entire network traffic, the entire system over the traffic, and this is done by basically saying that 2 files are similar if they are from the same original volume, and otherwise they are not the same. And those 2 metrics, both the Jaccard and the second similarity regarding the traffic, are combined as a weighted distance, and we use that weighted distance in order to decide which files we group into which cluster. The third and last goal is to balance the volume sizes. This is done by assigning a cluster max size, and when a cluster reaches its max size, we can no longer group any files into that cluster, and we move on to our second option, and so on. So every other aspect that you can read in the paper about how we use randomization, how when we decide the cluster max size and we fail to propose a valid migration plan, how we try to do it. All of this is presented in the paper. Our third and last approach is the integer linear programming approach, which is the ILP. The first thing that comes in mind is that this is a theoretical optimal solution. We want to achieve a theoretical optimal solution. So this is something similar to another paper from FAST20, and what's showed in there is that a very simple case, and we followed a similar manner. The entire system is formulated as an ILP problem. This ILP problem is then presented into an ILP solver to solve, and the result of the ILP instance is then translated into a valid migration plan. Because even the simplest form of this problem is proven to be NP-hard problem, we don't always get the best result we can have, and we desire the optimal solution, but in some cases we satisfy with any legal solutions that might not be optimal, but we hope that they are very close to an optimal solution. The three goals that we had are addressed by the first goal that we had to minimize the system size is addressed by the optimization goal for the solver, and the two other goals regarding the network traffic and the balance between the volume sizes are linear constraints. So they are all enforced with the optimization goal of the system size. Again, if you want to read more, you can look at the paper. So we wanted to compare between the three approaches. We have three different data sets. The first one is 500 Microsoft employees workstations. The second one is 9 weekly backups of 9 different users in the Stony Brook laboratory. And the final data set is the Linux kernel archive. Every single one of those data sets has a different number of files, and when we say file, we mean an actual file system. This is the granularity in which we migrate the entire the files in the system in our project. And these data sets were then we generated a sampled system from those data sets, and in similar manner that was shown in other papers, and we ran our approaches on the sampled system, but the results, the final results of the migration plan were then applied on the full system in order to evaluate our original cost. So in the paper you can see many more systems, different parameters, and the full explanation. In terms of reduction of the system size, so here we can see on the x-axis you can see the different data sets, and on the y-axis you can see the percent of the system that was deleted during our migration plan. Here we can also see that we have 6 different bars. Each approach has 2 different bars. The stripe bar is the approach without the load balancing constraint, and the other bar is just the same thing with the load balancing constraint. So we want to have as much we want the bar to be as high as possible in order to delete as much as we can. And we can see that the clustering process and the ILP approach, they are pretty much comparable. in some cases, even the clustering process deletes more percent of the system than the ILP. This is mainly because sometimes the clustering approach can get the optimal solution. In some cases, the ILP times out, as you can see with the red X above the bar, and therefore it doesn't get the optimal solution. Furthermore, we can see that the greedy approach is far behind, and it's not comparable to either of the approaches. Another thing is that the balance constraint that enforced on the regular bars, not in the star bars, it also makes us lose a bit of the system deletion that we originally had without the balance. This is reasonable because we want the entire system to be spread across different volumes and not the entire system inside one volume. In terms of runtime, we can see here on the y-axis the log scale runtime in seconds, where the red line is our time limit, our timeout, which is set to 6 hours. So we want to see a very low bar. We can see that greedy is by far the fastest approach. It is reasonable because it's an iterative approach, very simple one. And the clustering is the next on the list, and followed by the ILP that sometimes, as we can see both on Linux and Microsoft datasets, is timing out. One thing that we need to keep in mind is the clustering process is running a few instances of the algorithm, so the time that we see here is configurable, and it can be reduced in accordance to the order of solution, the type of solution that we want. If we want a better solution, that we might run a few more execution. The final metric that we wanted to check is the balance of the system. Balance is defined, we defined it by the minimum size of the volume divided by the maximum volume size of the volume. So when we want this metric to be as close as possible to 1. So here we can see on the y-axis the balance metric, and we have two other lines on the bar on the graph. So the blue line is the original balance of the original system, and the red line is the goal that we want to achieve with our migration plan. So what we can see that is the balance constraint. When we use it and apply it on the regular bars, we achieve a more balanced system. And when we do not use it on the stripe bar, in some cases, as we can see for the ILP and the clustering, we can see that on the Linux, when we do not apply the load balancing in the system, we achieve a system that is highly unbalanced, and we have almost empty volumes. So to conclude, migration in the duplicated storage is hard. We saw 3 approaches. The first one is the greedy approach, which is by far the fastest, but it's also very weak. The third approach that we saw is the ILP, the integer linear programming, which is optimal or close to optimal, but it takes a very long time. And in between them, we saw the clustering approach, which is close to optimal in some cases, and it's usually fast. As I said, it's also configurable and it can be reduced. So, thank you.
The times that you mentioned, are these the times to run the algorithm or the time to actually migrate?
No, it's the time to run the algorithm.
Run the algorithm.
Yeah.
And how does that compare with the time to migrate? Is it negligible or is it much longer?
We didn't test it. It's basically how to generate a migration plan. We didn't test how much time it takes to actually migrate the data.
And the related question is, this is a bulk. You need to migrate and decide what to send where.
Yeah.
In bulk. If you try to run an incremental kind of online,
yeah,
as the system works to decide to keep it balanced, it may cost nothing, because you would simply decide where to kind of keep it balanced as you go along.
You mean how you do it in an incremental way?
Yes, incremental as the system, you want to keep it balanced, okay. Why did you need to migrate in the first place?
Okay, in some cases...
Sometimes someone tells you have to, okay. But
yeah.
other times you just want to balance your system.
Yeah.
Then
so,
you run incrementally.
So the original idea is when you, for example, if you have you add another volume into the system, or you have a maintenance and you want to get one server down and to migrate the entire data for the time being, but for the purpose of the running the algorithms or finding a migration plan during during a running system, this is something that we are thinking about.
Okay, so just a final clarification. You need to migrate what? A volume, a bunch of files. What is the
so the granularity
setting?
Yeah, the granularity is file is a file system, the entire file system. So
okay, so you're told that you need to migrate file system X to a certain place.
You get the list.
You need to decide where to migrate. Well, I'm trying to understand the big picture.
Yeah, so the algorithms get the original state of the system, the entire volumes, and they decide. They say as the answer where to put each single one of the file, which is a file system.
To get a
so think of it as deduplication domains. That's a volume. And so you have your system is not global deduplication. It's built out of storage systems. You need to balance between them.
No, I understand. I'm just trying to understand what you're being asked to do in the first place. You have a current state, and now for whatever reason, someone tells you take this file system and migrate it.
No, that's the purpose of the algorithms. You don't do it by choice. You run the algorithms on the sample system.
No, but why are you changing from the current state to begin with?
It can have many purposes. As I said, you can have resizing of the system. I'm not sure I understand.
No, but
space
you have a current state, and you're just asked, please play with the granularity of full file systems so as to optimize something. That's the point?
Yeah, to minimize the system start. Yeah, we had the three goals.
And Sati, I should note that with deduplication, you don't know how to optimize when you place the volumes of the file systems, because data is going to pour in later on, and the deduplication relations will accumulate.
Yeah.
Yeah.
Maybe a short follow-up. So I take your algorithm, your plan, and I add other reasons for migration, like disk failure or anticipating a disk failure, and so on. When you speculate, how would that change the results? Would that make the problem significantly harder?
So I guess it will be much harder, but the basic principle is it's a static system. It's not a dynamic system. Maybe in the future it will be a dynamic system, but for now it's a static system.
So I have a question. You didn't show numbers on the actual traffic size. I mean, what was the difference, or did you ever reach the limit on traffic? And is there a kind of diminishing effect? If you want to improve now, you have to move a whole lot of data. I assume there's going to be some trade-off between how much traffic and how much space you're saving.
So basically, the results we showed here, they have a limit on the traffic, the network traffic. But in some cases, you can use a bit less traffic and get the same results. It depends on the type of the algorithm. In one case, the clustering algorithm can give you an optimal solution with as the IOP, but it will use less traffic, or the other way around. It's not something that is...
Did you usually reach the traffic limit, or was it far from?
It depends on the data set. For the Linux system, because the duplicate data is very large, we have 96%, I think. So with just 10% of the network traffic, you can move the entire system, because it's basically the same.
right now you're using to build the similarity matrix. You're using two metrics, right?
Yeah.
The question might be if you were to try to also optimize for peak traffic or reducing read latency and things like that. Would the hierarchical clustering approach still scale as you add more and more metrics that you somehow need to build into the clustering?
So the metric, the calculation of the actual similarity is something we do at the start, and when you start doing the actual process, is it something that you...
The question is not about the performance of the algorithm.
Okay.
The question is whether the quality would be maintained as you add more and more things into this single matrix that you only have one of them.
That's a good question. I don't know what to tell you about it, but it might be...
That's a good question.
Yeah.
Maybe
it might be worse, it might be the same.
Right, thank you.
Let's thank the speaker again.